late. So I got the videos up. Things are going well. I'm going to have to go kind of fast today to cover all the material that's on the problem set, or I'll have to cancel one of the questions. I'm not prone to doing that. So anyway, I'm sorry today. I'm just going to kind of have to hustle a bit. I normally like to take my time, obviously. Sorry about that. So of course your homework's up, the videos are up. I was a tad bit late on the videos just because it takes hours and hours to convert them to the weird format that the camera comes with. Get the doors, and so remember homework's due on Wednesday. I will. Sorry, I don't want to talk when I'm walking over there. The homeworks are graded. I don't know what the grades are yet. Again, I'll return them on Wednesday, so we'll have just a few minutes early. Again, I'll just spread them all out along the wall here. Try not to go too nuts, all right? And then remember, there's going to be mistakes, all right? So the grader sometimes, he'll just flat out see a question that's correct, and they'll just count it wrong just because his brain falls out of his head sometimes. And unfortunately, this being such a big class, it's probably going to be kind of painful for him to grade these, so I expect that he's going to make mistakes, right? That's all I'm saying. When he makes mistakes, try to see him. That's Xiao Han. His contact information is on the web. Try to see him to fix it because he has the grade book. If not, or you just don't agree on a resolution to whatever the problem is, then talk to me at that point. I'm not trying to duck anything. I want you to get your points, all right? That's kind of important. So I hope this is the right pen. See, somebody struggled last time with this. It doesn't look so good. Certainly, guy never freaking wipes out the board. So, anybody have any questions? We're all okay, right? We're doing fine. Okay. Now, recall that we're in the introduction to thermo, and we have this internal energy thing, which is heat plus work. And one of you asked me about the way I write my partials. I don't know. I know that there's different types of partials. If you're doing single versus multivariable calculus, I don't care. It doesn't matter. Certainly you're going to be fine. And also, thanks for keeping the volume folks down. You did really good. And by the way, that last Friday, that was actually the best Friday, the extra hour. That's the best extra hour I've had in like 2 years. Because I haven't had people ask me questions, but I think it's because I was actually stuck in 340. And 340, to be blunt, it's a lot of pre-meds. So their only question is, how do I get an A? They're a good group of people, but it's just I don't feel like there's a lot of interest, and I am getting that off of you guys. So this is fantastic. It makes me happy to come here. So, all right, anyway, all right, now I told you before that this is an exact differential. This is inexact. And it seems like my handwriting is still small. I don't know why. I'll try to write bigger. If you folks have trouble at top seeing, there's still seats down here if you have any trouble. Okay, so last time we talked about path integrals, and again, if you go to grad school and you learn a little bit extra math, everything turns into a path integral. And I know that sounds like, remember I said last time, that sounds nuts. What do you mean path integral? You just integrate the damn thing and apply the limits. But I showed you there is another way to do it. We did it really easy. I'm not gonna do it all over again. I'm sorry, I got halfway through this part before I just ran out of time. My head just fell on my brain fell on my head. So anyway, we calculated this. We integrated this thing along leg 1 and 2. We added them together, and we got. I think that's right. Yeah, we got 3. Just look at your notes, look at the video. And if we went down this path, and the clever thing here is we turned all the x's to y's, and we ended up with 2y change in y, and we integrated it along a path that x is equal to y, and we also got 3. That makes this an exact. So what that means is it doesn't matter how I got there. It doesn't matter the path taken. I could have done all kinds of wild paths, forward, backward, up, down. As long as I went from point 11 to point 22, this function, the evaluation of this does not change. So that makes it exact, path independent. As you see, this is exact, and we're going to do a lot. I know it's kind of like, yeah, okay, whatever. This is one of the best things that can happen. It makes everything really, really a lot easier. If it wasn't for this little factoid about exact and that this is exact, it saves us a heck of a lot of trouble. It makes things much, much easier, I promise you this. Okay. I should have said that, exact. God, I hope it. So I got 2 new pens on Friday, and I didn't know which one was which, so I may be screwing this up. Okay, now, here's an inexact differential. So a little bit harder. Sorry, not harder. What am I saying? What's a little bit easier? But as I'm going to show you, the path actually matters. So, the evaluation of 1 plus 2 will not come up the same as 3. Oh, and by the way, one of you asked me after class, this was very clever by the way, this person said, hey, wait a minute, so when you added these two, you said they were areas. Where exactly, the area is where on this graph? And I looked at it and I kind of got confused myself, and I didn't quite see it either. I'm like, oh, no, it's just a property of integrals that they can be added together. And that's true, all right? But then I realized the answer to the question was I can't show you the area. X, Y, that's basically Z. You know, it's just a letter, it doesn't matter. X, Y, Z. 2 dimensions or 3? 3. 3. It's a volume. I added volumes, not areas, so I kind of got that mixed up in my head. So it's very hard to draw this because really, you know, I've got the X and Y plane and then the F plane or Z plane is up. So I can't really draw it. That's why I kind of got confused there. But you know areas add, and so do volumes. So of course volumes add together. That's the definition of extensive. Okay, let's do this guy. And let me get, I'm not trying to cheat. Let me get my notes to make certain that I'm not screwing up. Let's see, this is a lot of Y. Y equals 1, Y equals 2. Red 1, right, okay. Okay, sorry, I should have had a little Y here. Y equals 1, Y equals 2 is Y dx. X isn't changing, so that's 0. Just to remind you why that is. There's no change in X, it's constant, right? Did I do that right? Yeah, I did it right. Okay. All right, let's do 2. You can still add together. Of course, it's just 0. Okay, Y dx. Let's see, Y is 2. And X is now X with limits 2 minus 1. And that's 2. So the total is 2. I hope this is the right pen. So these pens mature, and if I use it enough, it gets darker, or I'm using an old pen, and I don't know which one's which. Okay, now again, we'll make X is Y. Let's make Y dy. And X equals Y equals 1. From X equals Y to 2 is going to be 1/2 Y squared. Sorry, I'm writing this kind of funky, I don't know why. From 1 to 2. Okay. So let's see, that's going to be 4/2 minus 1/2. 2 minus 1/2. And that's 3/2. Right? So let me make sure I did it right. Yeah, 3/2. Okay. So, inexact. Sorry.
You still have to multiply by 1/2.
What's that?
You still have to multiply by 1/2.
No, let's see, 4 divided by 2 is 2.
Oh.
Right, and that's fine, minus 1/2, right, upper minus lower. Yeah, I got it right. So it's fine to ask. So that makes this inexact. So this is path dependent. Okay, so you're probably still thinking, so what? You don't look excited. So anyway, let me point out a couple of things. Okay, what's neat about this? Can anyone guess? Now I have the change in f. So I differentiated f. F is a multivariable function because it has x's and y's in it. And when I differentiated it, it looks like I took the chain rule, right? Or the product rule. No, chain rule. I forgot. Whatever. All right. Now, instead of changing f, I want to say f is equal to something. Any idea? It's very simple. What is actually? I've written you the change in f. Now I want to know what f is. What is the function of x and y?
X times y.
X, yeah, a lot of you got it. X times y. X dot y times whatever. I screw up dots and times. It's the same thing. Actually, dots technically dot products. We're going to get into that today. Okay, yeah, f is x times y. And you know, when I differentiate it, I'm going to take the derivative with respect to y, and that makes x constant. And then I add to that the reverse. So it makes total sense. And remember, that's as hard, that's multivariable calculus, right? It's just take the derivative twice and sum them. That's, wow, we're done with multivariable calculus. That really is it. It's so freaking simple. So now let's do this one. Sorry, I'm not using the board very well. In this case, what is it? A little harder. Again, cat got your tongue? I might buy a cat. Big stuff. I'm going to name her Dr. Tomorrow. That way I can be at home and say, no, Dr. Tomorrow, don't. All day long. So anyway, back to task. F is equal to anyone? No one? Y squared?
1/2 y squared?
It's a trick.
Why?
If you could answer this, you should win a Nobel Prize in mathematics. Except there is no Nobel Prize in mathematics. No one knows why. Can't even. Yes, I'm a Valley girl. So, no, you can't even. There is no function. The function does not exist. It exists only as a change in a function, but it is not a function itself. I'm talking about f. So, if you think about it, just try writing this down. Just remember that one rule about multivariable calculus. That if I have x times y, I'm going to have to take the derivative of 1 and hold the other constant, and then vice versa. Try to come up with a function of x and y that gives you this when you differentiate it. You can. Try it all day long. People have actually gotten supercomputers, because this is actually a theorem in math. It's not like a proof, it's not a law. But what I was reading up on this, mathematicians have never been able to get an exact differential into a functional form instead of a differential form. They've had supercomputers work on it, trying to find some elegant, esoteric mathematical function, have the computer generate functions that would do it, and they've never been able to find a function that does this. It seems to be, that's kind of their way of proving that this is true, that inexact differentials have no functional form. Okay, now back to actual physical reality. Here, I'll get rid of this. It doesn't matter. We did it from last time. Okay, now that I've told you that there is no functional form for an exact differential, have you ever seen a function that does that? Or, sorry, a change in a function. Anything like this before? No? Cat got your tongue again? Maybe I'll if I get the cat over into class. That way you won't pay attention to me. Seriously, think of one thing. Anything that has that form? Never seen anything like that before?
Work.
You're reading the book, aren't you? Yeah. Actually, work is force times change in distance. Of course you have. It also shows you work is an exact. It has the same, I mean, these are no different to me. And hopefully, because when I was at office hours sometimes, some of you are actually, I know you think this is kind of trivial, but some of you are actually still having problems with calculus when instead of x's, y's, and z's, you have p's and b's and t's. So, again, these are no different, so work is an exact. Heat is, I don't really have an equation for heat, heat just is, but I'm getting there, don't worry about it. So, anyway, and again, that's path dependent. Now, there's another thing that I'll bring up now, but if I have time, yeah, I have time, I'm going kind of fast. There's this other little mathematical principle about inexact and exact that's going to come up twice and later on, but I want you to go ahead and see it now and understand that this is going to come back. I'm going to do that a lot, by the way. Introduce something, let it lay down for a while, and then it comes back up, because I kind of want to just kind of nibble away at your mind here, get you used to this stuff. All right, so this is called the Euler criteria for exactness. Okay, probably this will be on the test. First test, second test, probably will be on the final. All right, so little star, and I'm going to keep trying to do this. I'm going to put little stars by some of the things you really got to know. Right now, remember I told you we have 48 equations, 48 different thermodynamic equations. You can't remember them all, it's impossible. So I'm going to keep it down. Things with stars, you remember. And there won't be that many, maybe about 10. And those 10 things give you the other 38 things. Right? That's how you have to do this, there's no other way. Right? What the Euler criteria says, that if something is exact, and since we live in a multivariable world, and there's just simply no choice about that, that this is true. Let's take the derivative of, let's see, let me make sure I'm writing it the same way. I'll stick with f. Okay, f is a function of x and y. All right, then we're going to do a double derivative. Again, with this funky kind of notation. Looks like this is a good pen. What the Euler criteria says is that the order differentiation, y with respect to x, take the derivative with respect to y at, what have I done? No, x, sorry. I'm going too fast. There we go. Okay, that's the Euler criteria. If a function passes this, or sorry, more accurately, I guess the change in the function, if a change in the function passes this test, then it's exact. So, and actually if you apply it to the above, you would actually see that, wouldn't you? Okay, I wonder if I can try this. I've never tried this before. If I do this first one, what am I going to get? I'm going to get x dy dx plus y, and the derivative with respect to y, dy. See, this gets wiped out because that's 0, and then I just have 1. And then, actually, yeah, the same thing would happen over here. All right, I don't know if you see how I did that. I just actually took that function, this guy, and I divided it by dx. I treated it like I'm juggling again, right? Just pure, very simple algebra is all I did. So I just divided everything by the change in x. So the change in y with respect to x. Now I'm going to call that 0 because they're different. They're 90 degrees, and I've defined them that way. And that left just the change in y with respect to y, which is 1, and in honesty, I don't even have to do it. The exact same thing happens there. So I've got 1 equal to y. And therefore, this function, this guy, is exact. It's another way to prove it. And it would clearly fail on the, I don't know what you get. No, I don't care. Anyway, so there you go. And again, this is going to come back 2 more times. Let's see, when we're going to do things called Maxwell relations. Maybe some baby thorough. Did some of the engineers see Maxwell relations yet? Yeah? I don't think it'll be bored to tears. Anyway, sorry, chemists, you have not seen it. I don't know if you knew this, but what do you engineers? Do you take thermo 3 times?
Yeah.
Oh, I heard that. Yes. Well, I think it all lays then. That's the opposite. I make mine great and a lot easier. Okay, so then, all right, so again, the order differentiation doesn't matter, and just remember that it's coming up again. Now I want to talk about U, and I've already brought this up, but I need to bring it up again. That's internal energy, and this pen just looks terrible. I hope you're not having a hard time reading it. Okay, so internal energy, I explained this before. If take something like xenon, which can't rotate or vibrate, then the only energy that I care about when it comes to thermo is, because I'm not going to treat it like nuclear fuel, I'm not worried about it decaying into another element, which it will do eventually. All elements turn into hydrogen eventually, and that's how the universe comes to an end. Everything turns into a dilute gas of hydrogen. Kind of sucks, doesn't it? But that's what they say is going to happen. And I'm not worried about that though, because I'm just not worried about it. Because I need this to power my car. It's fuel for my car somehow. And in which case I only care about its translation. It's pressure. And I'm going to use pressure to drive the car, which I can do. It's not a good idea, but it can be done. So that would be the internal energy of something like xenon. It's just its ability to translate, bounce off walls, and that's pressure. And I need pressure. Pressure pushes things. Pressure makes things move. Okay, so the way I would know what internal energy is, this is one way you can do this. You literally can do it this way. It's stupid, but it can be done. Take a xenon atom and freeze it, so it's probably going to stick to the wall somewhere. And then you have a metal box, and you're surrounded by insulation. And we're really good at this, by the way. This is like our oldest technology. And then what we can do is sneak wires into the box, and we can use that to heat the box. And what you do is you just measure the amount of current. I mean, it's easy to measure the amount of energy that goes through the wires. And that energy turns to heat. So I know exactly how much energy is going into the box, right? It's a calorimeter. Our best instruments that humans ever made are electrical calorimeters. They work fantastically well with, like, they can measure something like 1.00000 kilojoules or something like that. Not much lower than that. It's kind of ridiculous. But again, we're very good at calorimetry. So what I can do is heat the box to room temperature, and I know how much energy went into it. How much energy it took to unfreeze that xenon, and then eventually, it's a gas, so it starts bouncing around. And I heat it up some more to room temperature, and it's bouncing around kind of a lot now. And I knew exactly how much energy I put into that box to get it to room temperature again. And and take into account the box itself. Again, however, it would very well. So that would be the internal energy. So, what about that? It turns out that for monatomic gas, the internal energy is going to be 1/2 m, and this is that thing again I told you about that I didn't talk about this semester. If I'm in year 346, which is unlikely, by the way, but if I end up teaching 346, I will tell you how to calculate this. And it's a bear, all right, but it's doable. What I would have, I have 3/2 RT. And again, I'll make temperature 298. That would be kind of a smart temperature to raise something up to. That would be practical. So I find this relationship. All right, it turns out that this is more general than you might think. This leads to what's called the equal partition. Okay, let's start by this one, by the way. Equal partition 0. Okay, this is the ground floor of thermo. All thermo builds here. It starts here. And I wish I could show you this proof. That's why I normally teach Maxwell-Boltzmann distributions to prove that. And unfortunately, since we'll do it in 346, you're going to have to take a little bit of a leap of faith that this is exactly correct because of this thing here. From the, again, Maxwell-Boltzmann. Equal partition theorem says, pick up, sorry, I can't spell the word pick up 1/2 RT per degree of freedom. Thermo's a Republican. Anyway, so degrees of freedom. So for every degree of freedom you pick up, and you're probably thinking, what the hell is that? Hold on a second. For every degree of freedom, add 1/2 RT of internal energy. And this is, again, that's the internal energy. It goes to the internal energy. Now you might recall, God, you engineers hope you're not bored to tears, but you may recall that there's things like enthalpy. For you chemists, you're going to pick up a new one called A, it's Helmholtz energy, and then you got Gibbs energy. So those are built on top of U in kind of an odd way, called the Legendre transform, which we'll get to pretty soon. And, sorry, I do need to speed up because I've got to answer that question. I want to do your number 9, or number 10. Okay, so let me show you what a degree of freedom is by example. I think that's the best. Let's talk about a gas. Talk about certain gases, and I like gases because it's just easy. Degrees of freedom. Degrees of freedom, and then what is U? Now we're going to say U is equal to U0, and this is temperature, plus ... We're about to add ... Now what we say is U0, I'm just going to, in this class, I'm going to treat it as 0. But just so you know, even the frozen xenon, it still has, I'm going to say it has no energy. I'm just going to decide that. But really it does because it can go nuclear on you. You can split a xenon atom, and if you do, kaboom. All right, but again, this is a nuclear weapons class. It'd be cool if it was. I got a nuclear weapon, by the way. Actually, I have a good friend, a guy I went to high school with. He was actually like my math buddy. He ended up becoming like a lieutenant colonel. I think he's still in the Air Force. His job, because he's a smart guy, his job is to talk to nuclear weapons designers, and they tell him what they want to build, the machines of death, and then he goes to explain it to the top brass in ways that they can understand, because, they're not nuclear engineers. So anyway, I asked him once, I said, hey, dude, tell me how to build one. He's like, man, just look it up on the internet. He's like, the plans are all out there. Actually, this guy reverse engineered Little Boy. That's the one that we dropped on Hiroshima. This guy reverse engineered it from photographs and put up the entire details on the internet. What a hero. That is kind of bad, really. Okay, let's do argon or xenon. Okay, now again, I want to explain what are degrees of freedom, and it's just easier to, by example, so we can translate. And we live in a 3-dimensional universe. And, I kind of like to read like Stephen Hawking type of stuff. I'm not, it's not like I can read like physics journals. I would just have no idea what the heck is going on. So I get like Stephen Hawking has written several books, and it kind of explains it to a layman, how all this stuff works. And they think that one possibility, the reason we live in 3 dimensions is that we were born in 4 dimensions, and that we are on the skin of a black hole in a 4-dimensional universe. And because we exist on the skin of this black hole at the event horizon, you lose a dimension, and hence we live in 3 dimensions. Anyway, I just think that's cool. I don't think this guy has really any idea. Their theories change all the time, too. Okay, so half, half, half. Half, 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 3 halves. RT. And again, I'm ignoring the energy at 0 temperature. I'm just going to call it 0. Okay, CO2. Okay, so this is easy. Oh, no, wait a minute. So, got to back up. Why not run, can the argon vibrate? No, that's ridiculous. That's actually not quite totally right. But anyway, I'll get there. Maybe Wednesday or Friday, I'll explain to you that maybe it can vibrate, but it's kind of funky how it does it. But for the most part, we're not going to think about that. Only X, Y, Z. Now, vibration and rotation. Those are the only other degrees of freedom I can think of. I mentioned this before, can I rotate argon? Can I shrink myself, pick it up like a bowling ball, and can I do that? Because I can't shrink myself? What have you said no? The answer is no. Any ideas why? I think I kind of hinted at it. It was last week.
Because you can't know position and velocity.
Quantum mechanical principle. Actually, this is very simple. If you think about how much energy, you can kind of roughly calculate this. We call this the back of the envelope calculation. The kind of thing we have to do in PhD exams. All right, so nucleus is here. It has so much charge. The electron has an electron's charge. Now, this thing, basically, you can kind of take a Bohr model of the atom, which isn't totally correct. It isn't correct at all, really, but this kind of works. You can think about how much kinetic energy does it need to not slam into the nucleus. The reason it doesn't slam into the nucleus is because of pure quantum mechanics. It says it has no chance of ever, the electron's whizzing around somewhere, but the probability it's ever at the nucleus is 0, and quantum mechanics says that. So the electron never crashes into the nucleus, and that would result in catastrophic explosion. So argon isn't exploding at any given moment, but you can kind of roughly see how much energy does it take to whiz around and not fall in. And that's actually kind of a good number for how fast the electrons are moving. What do you think, slow or fast?
Fast.
Extremely fast. Their kinetic energy is actually gigantic. So what does it mean to pick up an argon atom, think of it like a bowling ball, and roll it before it's even turned slightly, those electrons, which is what I feel when I hold it, those electrons have already spun around it a bazillion times. So that rotational, my perception of rotation to it means nothing. Because again, the electrons have already whizzed around it a bazillion times. So no rotation. It doesn't count. Now CO2. You got, sorry to do it this way. Now I think CO2 is different. So I at least have 3 halves RT. Anyone? Can it rotate? All right. Can it do this? All right. You can do rotate this way, rotate this way. These are different. They're technically in orthogonal dimensions, and that means that each one counts separately. Okay. Can it pirouette? Pretty surprised I could do that. Can it pirouette? You should see what I'm wearing underneath. Oh, anyway. All right, but seriously, can it pirouette? Anyone? How different is that than one vote yes?
No.
And you're guessing because of my body language, but it's no different than rolling the argon atom. So this, but not this. This does not count. That's like trying to bowl an argon atom. So it's got 2 rotations. Vibrations. All right, you remember your 3n minus 5, 3n minus 6? How many? You have a number? How many vibrations? Any idea? So remember 3n minus 5. You had this in freshman. 3n minus 5 for linear molecules, 3n minus 6 vibrations for nonlinear. Linear 3n minus 5, nonlinear, which is those things 3n minus 6. So this has
3. 3,
3n, this is 3 atoms. 9 minus 5,
4,
4, has 4 vibrations. 1, 2, 3, and 4. There you go. That's how it does it. So, and the way you actually know that is actually, unfortunately, very complicated. Those are called normal modes. You'll actually learn a little bit about that in 346. It's a topology theory phenomenon. It's unfortunately really quite hard to understand, and I hate that, but it's true, to know what are modes, and again, these are non-overlapping modes, and that means that you have equations that describe the motion, it describes the motion, and when you integrate that times an equation that describes another motion, you get 0. All right, so anyway, that's how you know that those are called normal modes. That's how, again, all the ways it can legitimately move that are orthogonal or independent of each other. So that way you can plot those modes as like X, Y, Z. You know, this mode, that mode, that mode. So anyway, I'm prattling on and on and on. Okay, so plus 4 vibrations. Okay, 3 halves, 6, 7, 8, 9 halves. That's easier. 9 halves are. Okay, methane. 3 translations plus how many rotations?
None.
Not going to be 2. I eliminated 1 when we came to CO2 because it didn't count. But methane is nonlinear. 3n minus 6. Well, so yeah. Hold on, 3n, hold on. All right, 3n minus 6, so that's 5 times 6. So 5 times 15 minus 6 is 9, right? Did I do that right? Yeah, 9. So, and sorry, brain just fell out of my head. Rotations. I don't know why I said about rotation, I said talking about vibration. Sorry, I'm being an idiot. Any idea how many rotations have I got? No, 3. You have 3 rotations. Okay, now that's easy. If you're wondering why, that's easy. It's because we live in 3 dimensions. So nonlinear molecules, atoms can rotate. Linear molecules can, but you have to eliminate one of the rotations because it's the same thing as rolling an atom. And then methane, since it's, it has symmetry, but picking up picking up argon will feel like a beach ball, and then this feels like a stick, and this would be kind of like a spiky thing that would kind of be like ouchie. So again, because we live in 3 dimensions, we have 3 rotations. So 1, 2, 3, 4, 5, 6, 4. Is that right? 15. What happened? I'm just counting something. 15. What do I have? Yeah. Sorry, 15. Yeah, 15. My bad. 15 and a half argon. Okay. Anyway, so I hope that gives you an idea of degree of freedom, translations, rotations, and vibrations. And what that means is, excuse me. It's kind of something in my throat. It means that these things can store energy, essentially. Oh, sorry, excuse me. Just got a tickle in my throat. So whenever something warms up, it's going to take that energy and use it. It's going to use it to bounce off the wall. It's going to roll around, and it's going to vibrate with that energy more and more. All right, so that's just like, think of this also as heat capacity. It's going to suck that energy and do something with it, and that's kind of heat capacity. And the more things it can do, the more energy it sucks in before it heats up, because you just won't perceive it. Again, it's an energy sink, and you put a little bit of energy, this guy gets hot. You have to put a little bit more energy into this guy to get it hot, because it's going to do so much with it. And this guy, you have to put a lot of energy to get it hot, because it has so many things it's going to do with that energy. It's kind of like anticipation, but there's a problem. Here's a slight problem. So, as I mentioned before, there's a preference 346. Let's think of quantum mechanics. Sorry, a little water. Let's talk about, let's just do a diatomic, so O2. And you know its vibrations would be something like this. So it can, it can do this, it can do this, or it can do that. So anyway, so it has a couple of ways of vibrating. Now this will represent the average distance between two oxygens. And this way, it's like they're getting closer, and this way they're getting further away. So it's, it's this motion. This motion. Sorry, I'm being an idiot. I'm sorry. These are translations. I really drew this wrong. Those would count as translations. My bad. Anyway, all right, so we're squeezing together, we're expanding. We're squeezing together, we're expanding. All right. Now, quantum mechanics says that, as I mentioned before, and I'm kind of surprised how many people don't actually, you haven't heard this yet, and I'm a little bit taken aback by that, that's not your fault. But when I'm in this cage, I can't move at any speed. I know you see me speeding up, and it looks like I'm very continuously speeding up, but I'm not. I'm actually going this fast, then I'm going this fast, and then I'm going this fast, and then I'm going this fast. I'm speeding up in jumps. And again, it's because I'm in a cage. When you take 346, you're going to stand wide. Cages, everything's in a cage. God, isn't that depressing? Your bird's in a cage, but we're all in a cage of some kind. And the cage is where you get quantum from quantum mechanics. It's a boundary condition. Boundary conditions mean that when I'm in this cage, I'm actually not moving. I'm not speeding up continuously. I know I looked like I was, but I wasn't. It's just that making the measurement of how fast is this versus how fast is this versus how fast is this, you can't do it. It's just too hard, but it's there. So, what does quantum say about vibrations? Okay, that everything's always vibrating. You can't ever stop something from vibrating unless you cool it to absolute zero. But you can't cool things to absolute zero. So this is how much it's vibrating. Now, I dump a lot of energy in, and right when I've added just the right amount of energy, it does this. And then I add more energy. And then all of a sudden, it's going to go this fast, and it's going to keep going this fast. But then when I add just the right amount of energy, it does this fast. It comes in jumps. And these are the jumps. So these are vibrational quantum levels. So we tend to draw it like this. Oh, God, what is this? Wonderful board. So you notice I didn't draw the line at the bottom. Again, when you have quantum, you're actually going to cover this in great detail. The fact that the line isn't at the bottom means that there's what's called zero-point energy. Again, prepping you for 346. Everything is always vibrating no matter what. And then this, it's vibrating faster, and it's vibrating faster. Now, excuse me. Now here's the damnedest thing. Sorry, I'm going to draw this really, really small. I hope you can kind of see what I'm drawing, or look at the video. So RT is kind of like that. What I've drawn is a tiny little bracket. If you're having trouble at the top seeing, I just drew a tiny little bracket. Meaning that the jump from here to here is very, very large. For almost all things, really just about everything. The jump is gigantic compared to room temperature. So, everyone look at this at room temperature. Okay, meaning that effectively, the way you see this expressed, and let me express it that way, is that vibrations are frozen out. That's the word, they're frozen out. So in other words, I've taken anything you can think of, any diatomic, nitrogen, oxygen, the famous ones, or methane, whatever, and I warm it to room temperature. Reality is, it always stayed in this quantum level. It always stayed at the ground vibrational state for all of its 9 vibrations. They never absorbed energy. If they don't absorb energy, then so what? Right? Who cares? They didn't do anything. They never acted as a sponge. If I had more energy, if I could impart more energy, eventually they do. Eventually they suck up that energy and jump from here to here. And then that's great, because then I can cool it down and it'll give the energy back, right? This is an energy reservoir. That's what all this translation through rotation and possibly vibrations, but not really. They're just energy. It's like energy banks. You put energy in, and then you can take them back out some other time, which is what thermo is. So that means that, except really in a rocket engine, and we're not really designing rocket engines, maybe some of you will. Actually, one of my former grad students, she is actually a rocket scientist. Her sister works at, what is it? There's a space flight center in Mississippi anyway, so she actually tests rocket engines. So I think that this is a concern literally for rocket engines, but we're not gonna do that, right? I don't even think the combustion in your car gets hot enough for things to absorb energy via vibrational excitation. Okay, long blah, blah, blah story. My point is that the vibrations don't count. They can't. They never take energy, they never give it away. If that's the case, then why am I bothering? So this ends up still being 3 halves RT. And this guy, all right, if I take away those vibrations, it ends up being 5 halves RT. And let's see, if I take away 9, that must be 6 over 2 or 3 RT. All right, that is really crappy. I'm obsessed, there we go. Okay, so weird reasons, this ends up being, monotonic gas, linear CO2, everything else. This would also, this guy here, this would also be O2, M2, all the diatomic gases. That's the only two we really care about. And then again, this is everything else. CO2, M2, O2, everything else, noble gases. Right, and this is their U. And again, so this guy again is the entirety of this is the foundation of all thermo. So this guy is really important. I'm definitely having equilibrium theorem on the test. It'll be on your next homework quite a bit. There's a lot of things you can do with the equilibrium theorem that I'm not showing right now, but I will. So anyway, so that guy is really horribly important. Last but not least, so that's what U is, but now I also said that you change internal energy by doing heat and work, and I do not think I will be able to get finished. So I'm going to have to cut, I'll email you all, I'm going to cut one of your questions on the homework, because I don't think I'm going to make it. Well, let's see how far I get, and I'll email you all. By the way, about 10 people have dropped and 15 people signed up, so my email list is shot to death. So what I've done is I've recreated it. You know, when I log on to the thing that I check, check UL and not Facebook, university registrar, so that I know who you are, so I can make a grade book. Really, that's all I need. It's the same thing that I used to input your grade when we're done. It also has this little option that says, generate email list. So I regenerate the email list, meaning 1 or 2 people probably aren't on it. So I'll email you right after class. If you don't get my email, email me back immediately. All right? So I know I've already done this once, but we're going to have to do it again. So anyway, look for that, because I may just have to cancel one of the questions, and it'll be on the next homework set. I'll give you a little bit of a break. Let's just see how far I get. Okay. So now, remember, I can't ever express work. I can't express work as work is equal. I can only do change of work. There is no work, only a change of work. And that's because it's inexact. And there's lots of ways to express work. The way the book describes it, if I recall, it's been a while since I've read the book. I did read the book, by the way, so I'm not going to teach without having actually read the textbook. Some people do that. Don't quote me on that. Okay, so I'm going to draw a lot of plungers in this class. So this is a piston. The piston has a plunger and a void volume. And we're going to add a force. Oh, dear God. I do have a backup pen, I think. For whatever reason, even if this is one of the new pens, it seems to be dead. Sorry about that. I've never had so much trouble with pens before. I've got 2 more. Anyway, okay, so the way the book describes it, work is anything that you can use to raise a weight, is how they like to put it. And what I add on there is anytime you're basically expanding or contracting a gas, that's work. Whether you're doing it by pushing or pulling, whatever, that's work. As long as the plunger moves, that's another thing. The plunger has to move. Or if you imagine you've got this little plunger deal, and you're pushing as hard as you can, but the pressure you add is matched because you compress the gas. The plunger's not moving, even though you're exerting, you're not forcing, you're not working. Right, so the plunger has to move. It's a little trick question I tend to have on homeworks or sometimes exams. I don't know what I'll do. Anyway, I haven't figured it out yet. So anyway, so the plunger has to be moving, but as soon as it is moving, you're doing work. And now we have to come up with a definition. So I'm going to say, again, there is no, oh my God, that's a hell of a lot better. Sorry about that. I didn't know that it was so screwed up. Times, so let's say that this guy, So what this represents is that we're going to move this plunger. We're going to push it in and pull it out. We're going to try both. All right, so now here's the thing. It's kind of hard to work with this. I don't like this because I like pressure. Pressure is easy to measure, and it's just kind of natural to think about, you know, if you compress this thing, that the inside has been pressurized, and or if you pulled on it a little bit, maybe the inside's become depressurized, you know, whatever. And so again, you hear that word pressure. I like to think in terms of pressure. It's just easier. And pressure is force over area. Now here's the damnedest thing, is that this plunger has a certain area, I'll just call it A, which is of course measurable. And so all I have to do is get the pressure times the area, and now I've got the force. So pressure times area. And by the way, this is a dot product times its motion. Okay, so again, you have to dot force into distance because they can be at asymmetric angles. Not so much in this case. Just a little factoid to keep in mind. Okay. Area times this distance. It's got a word.
Volume.
It's volume, right? It's the volume. So P. Now this is external pressure. I should have mentioned that before. Of course, this is the external pressure because if the external pressure, it's easy to think about compression. If the external pressure is high, the plunger will collapse. And it will do so until the interior pressure matches the exterior. But notice it's the exterior that's really doing everything. So that's going to be exterior pressure. Oh, sorry, I didn't know I did that. Times volume, change in volume. This is a times at this point. Cosine of the angle in between. Cosine of the direction of motion. So when I define, this is IUPAC definition, I define this way as an angle of 0, and if I'm pulling, then that's 180, right? So it's either in, the angle is 0, or pulling out, which means the pressure is at 180, and that's how you produce the pressure. Okay, so notice that, let's do contraction. So I'm leaving a space here. We'll see why in a minute. Now, times certain change in volume. Cosine of 0 degrees is what? 1. All right, but the change in volume is positive or negative? It's negative, right? It's a contraction. Let's do expansion. Let me write this down. PEXG, change in volume. And of course, if it's finite, if we're talking about a very small change, I'd like to put it like this. Remember, this is infinitely smaller than that to integrate to figure out whatever. Let's do expansion. Okay, work, change in work, equal to exterior pressure, notice I've left a space, times delta V, which is now positive, times cosine, what's cosine of 180? It's negative? Let's just do that. Equals minus PEXT, delta V, or, again, for a very small change, because that's symbology. It really isn't important. So there you go. I mean, the important thing here is that no matter what, actually, if you guys don't mind, let me just hold you one extra minute so I can do the question. I can just basically straight out answer the question the problem said. No matter which way you look at this, you always seem to be picking up a negative sign. So IUPAC decided that they would define work, and there's all kinds of work. There's pulling a string, rubber bands, you think of all kinds of work, pulling on a rubber band, but I like gas expanding, gas contracting, and when you talk about gas expanding, gas contracting, IUPAC decided to define it as negative exterior pressure times the change in V no matter what, for those very reasons I just stated. But it means work does some really funky things. All right, now last bit, so I can answer that question on the test. There's two ways there's a reversible work, where, just hold on, folks, I'm sorry, let me tell you this really quick. All right, there's two ways to do this plunger work. There's one way where you basically slowly pressurize the plunger here, and slowly add force to it, such that the interior pressure is matched to the exterior pressure, and I won't call that P, I'll just call it P, and that's called a reversible process. So if we graph that, because basically we're going to follow, what is it, Boyle's law, I think? Or Charles, I think it's Boyle's law. So, sorry, this is B. So the exterior pressure is always slowly increasing, always to match the interior pressure. As soon as that happens, I add a little bit more force, and so the plunger moves a little bit more, and then it stops, and then I add a little bit more force. And so the pressure inside is equal to the pressure outside. So this is exterior pressure, but it's the same as the interior pressure. And I know that PV equals nRT means that pressure is going to change the volume like 1 over X. Okay, now work is end up, if you want to integrate the change in work, it's going to be the integral of PdV, not exterior pressure, minus PdV. And so it integrals, again, our areas, and this one, since I only have 2 dimensions, I can draw the area, it's this. Okay, so this area times minus 1 ends up being the work. And ends up being most, let me write here, most negative work. Okay. Irreversible is a sudden exterior change. Now this is conceptually very easy. My plunger is at 1, this is at an atmosphere, the outside is at 1 atmosphere. Very quickly, I apply 2 atmospheres of pressure, and of course the volume goes down by about half. I do it very suddenly. And so, sorry, I did an expansion here, didn't I? I did a contraction. Right, I started here and went up. Okay, so, if I plot this here, well, how can I do this? Actually, sorry, let me do this. Let's actually do an expansion, because that's on your homework. An expansion. Expansion is negative work because this area is positive, and then I pick up a minus sign. Okay, real quick. Now, another way to do this irreversibly was I would suddenly change the pressure, lower the pressure, and then it would then automatically expand to here, and then this is the area under the curve. So this area is obviously less than the area. This irreversible is obviously less area than this reversible. And so then you put up a minus sign, and so the area for the reversible times minus 1 is more negative than this area in the irreversible times minus 1. Okay, so anyway, 2 ways to do this. Let me just actually answer your homework, because I feel really bad that I'm going way too fast. If you do an expansion, this is the homework question, by the way. If you do an expansion, you're going to get, sorry, compression. This is a compression, my bad, compression. So that's your homework. This is a compression. I've slowly added force to compress the cylinder. This is an expansion. Right, expansion, this is a compression. Okay, now to compress, this is the reversible, and it has this area. And then irreversible ends up being this. Right? This is when I suddenly increase exterior pressure, and it has this area. Now, the point is that reversible is always the most negative. But I'm looking at this, and I see more area in the irreversible. Right? More area in the irreversible than the reversible. But I'm telling you that the concept I'm trying to get across is that reversible work, and I'm proving it with these graphs. These are the proofs. I'm proving it with these graphs. Reversible work has always got the most negative area. But it doesn't look to be the case here, right? That looks completely contrary. There's clearly more area in the irreversible. Now here's the trick. I'm integrating, so I'm showing you an area, But now, I integrated from A to B. This integral is from
B to
B
A.
to A. What's the relationship between A to B of whatever,
Negative sign.
B to A, you just said it?
Negative sign.
Right, reverse sign. Now, what's more negative, 3 or 5?
3.
3. 3 is more negative than 5. It doesn't need to be a positive number. It's still more negative. There, I just answered the question. Okay, so, sorry I held you over so long. I'll make it up on Wednesday. Sorry about that. Email me with questions about health sales tomorrow. 12
Yeah, but I mean, we're already going into budget for so I figured like, oh, next year, if you do these 4 different kind of programs, budget state. Oh, no.